This is Chapter 23 of Physics 102B homework at Porterville College. We start with number 24. What is the energy of a photon with a wavelength 590 nanometers? So we need this in meters, kilograms, seconds, MKS units. So we'll have 590 times 10 to the negative 9 meters. We'll use the formula for energy is Planck's constant times frequency, or Planck's constant times speed of light divided by wavelength, because frequency is speed of light divided by wavelength. And there are the numbers that you plug in, and you get 3.37 times 10 to the negative 19 joules. To convert this to electron volts, we'll multiply by the conversion. 1 electron volt is 1.602 times 10 to the negative 19 joules, and we get the answer of 2.1 electron volts. Number 25, the momentum of a photon with wavelength 600 nanometers. Momentum is Planck's constant over wavelength. For wavelength, we need 600 times 10 to the negative 9 meters, and we get 1.1 times 10 to the negative 27 kilograms meters per second. Number 27, if they're all traveling at the same speed, which particle has the shortest de Broglie wavelength? De Broglie wavelength is Planck's constant divided by mass and velocity. That's from the book, equation 23.9. And so if wavelength is proportional to 1 over mass, then the shortest wavelength is going to be the one with the largest mass. So very roughly speaking, a proton is about 1 atomic mass unit, a neutron is about the same, a little bigger, but about 1 atomic mass unit. An electron is much smaller than those, about 1 over 1840 of an atomic mass unit. An alpha particle, which is the same as a helium nucleus, is 4 atomic mass units. And therefore, since it's the largest of those masses, it's going to have the shortest wavelength. Number 37. Tungsten light bulb, 3000 Kelvin. What is the median wavelength it emits? And if it's 100 watts, what is the filament surface area? All right, the equation for median wavelength is 4.107 times 10 to the negative 3 meters kelvins over the temperature. We plug that in, we get 1.37 times 10 to the negative 6 meters. That's in the infrared. If you go back to chapter 20, there's a chart that shows the approximate wavelengths and frequencies for all the different parts of the electromagnetic spectrum. And there's another chart that specifically tells you the wavelength range for every visible color. So you can refer back to that to answer some of these questions. So this is infrared. We have, for part B, if power is emissivity times the Stefan-Boltzmann constant times area times T to the 4th, we solve that for area. And we plug in 100 watts, we're going to take emissivity to be 1, Stefan-Boltzmann constant 5.67 times 10 to the negative 8, divided by 3000 to the 4th power, and we get 2.18 times 10 to the negative 5th meters squared, or 0.218 square centimeters. Number 38, we've got 20 kilokelvin, that's 2 times 10 to the 4th Kelvin. We're looking for the peak or the maximum wavelength. The peak wavelength is 2.898 times 10 to the negative 3 meters kelvins divided by the temperature, and we get 1.4 times 10 to the negative 7 meters, or 140 nanometers. That's in the ultraviolet. And the range of ultraviolet is from about 10 nanometers up to the edge of violet is about 400 nanometers. Number 41, we have a temperature and a power. We're given a new power And more importantly, we're told that the power doubles. And what is the new temperature? A good technique for solving this is to take the equation that relates power and temperature and put everything that's going to vary in this problem to the left and everything that's constant to the right. So we have P over T to the fourth equals epsilon sigma times A. Epsilon sigma times A are constant, and so I'll write it this way. P over T to the fourth equals constant. Now the technique that I'm going to use here doesn't, we don't care to solve for emissivity times sigma times A. We don't care to solve for that right-hand side. All we care about is that it's constant. So if P over T to the fourth is constant, let's set it up this way. The original, P naught over T naught to the fourth, equals P1 over T1 to the fourth. When we solve that for T1, well, let's solve it for T1 to the fourth, we get that it's T naught to the fourth times P1 over P naught. Now we're told, we can plug in P1 and P naught as being 900 over 450, but more importantly, it says that it doubles in power, so we can just say that's times 2. So T1 is T naught times the fourth root of 2. That goes from this equation, which is solving for T1 to the fourth, but I take the fourth root of both sides. And so we have 800 Kelvin times the fourth root of 2, and we get 951 Kelvin. Number 53. Find the energy of one quantum of microwave radiation with these two frequencies. So here's part A and here's part B. For 1 gigahertz, that's 10 to the 9th hertz, we just do energy for one quantum is Planck's constant times 10 to the 9th hertz. We get 6.63 times 10 to the negative 25 joules. Converting that to electron volts, we get 4.13 micro electron volts. For the higher frequency, it's the same 300 times the original from part A. We get an energy of 1.99 times 10 to the negative 22 joules, which comes out to be 0.0012 electron volts. For number 56, we have a three-parter here. Find the wavelength of a 4.1 electron volt photon, also for 2.3 electron volts and 0.69 electron volts. We're going to want to convert this to joules. So 4.1 electron volts, here we have it, times 1.602 times 10 to the negative 19 joules, and we get 6.568 times 10 to the negative 19 joules. We're going to use the formula energy is hc over lambda, which means lambda is Planck's constant times speed of light divided by energy. When you plug in the values, you get 3 times 10 to the negative 7 meters, 300 nanometers, and that's in the ultraviolet. It's just shy of violet. For part B, 2.3 electron volts, convert it to joules, as I've done here. Plug it into the equation and we get lambda is 5.4 times 10 to the negative 7 meters. That's 540 nanometers. That is visible light, and specifically it's the color green. Part C, lower energy, 0.69 electron volts. There we get 1.1 times 10 to the negative 19 joules. Plug it into this formula for lambda, and you get 1.8 times 10 to the negative 6 meters, or 1800 nanometers, and that is infrared. Number 66. We have a hydrogen atom, and it's emitting a photon, 434 nanometers, which is kind of between blue and violet. and I've drawn it there with purple for the color. We need to find the photon's energy and momentum. Energy is Planck's constant times c over lambda. We plug in those values. Lambda is 434 times 10 to the negative 9 meters, and you should get 4.58 times 10 to the negative 19 joules, or 2.86 electron volts. Momentum, quickest way to do that is to recognize momentum is energy over the speed of light. So 1.527 times 10 to the negative 27 kilograms meters per second. Part B, conservation of momentum, says the momentum of the atom is going to be equal in magnitude to the momentum of the photon. They're going to go in opposite directions but have equal magnitude. So that's the same as we got in part A. I've rounded it off here. So 1.53 times 10 to the negative 27 kilograms meters per second. To find the energy, the kinetic energy of the recoiling atom, we should remember that kinetic energy is 1/2 mv squared. We don't know directly what the v is. We could solve it, but let's turn this here, excuse me. Let's do it a slightly simpler way. If momentum is mv, then v is momentum divided by mass, and let's take that v, momentum over mass, and substitute it in to this v squared. And so we get energy is 1/2 m times, instead of v squared, we've got p squared over m squared, and that becomes p squared over 2m. So kinetic energy is p squared over 2m for the atom. We know the momentum, we got that in part B. Mass of a hydrogen atom is about the mass of a proton, 1.67 times 10 to the negative 27 kilograms, and we get 7 times 10 to the negative 28 joules. We compare that with the answer that we got in part A, 4.6 times 10 to the negative 19 joules, and it's about 9 orders of magnitude larger, or smaller, I should say. So it's much, much smaller than the energy of the photon. Whoops. That's physics for you. Okay, number 67. There we go. Number 67, find the energy needed to produce a proton-antiproton pair. Energy is mc squared. These two things have equal masses, the proton and the antiproton. So we're going to say the energy needed is twice the mass of a proton times c squared. There's the mass of a proton, c squared, we get that 3.01 times 10 to the negative 10 joules, and it comes out to be 1.876 times 10 to the 9 electron volts, or we could say 1.876 giga electron volts. Find the energies of the two photons produced when a proton and antiproton at rest annihilate. When they annihilate, they will emit two protons of equal energy. So we take the answer in part A, divide it by 2, and we get 938 mega electron volts in each of those photons. Number 69 is next. Okay. Find the speed of an electron with de Broglie wavelength 1 nanometer, the de Broglie wavelength of a proton with that speed. De Broglie wavelength is Planck's constant over mass and velocity. So velocity is Planck's constant divided by mass and wavelength. Wavelength is 10 to the negative 9 meters. And so we'll plug into this formula, V equals h over m lambda. And you should get 7.3 times 10 to the 5th meters per second. Now for part B, I've solved for lambda, but I've used the non-rounded off answer that my calculator gave me. Instead of 7.3 times 10 to the 5th, I have the full 727,333, so I don't get propagation of error from rounding. So lambda, I'm using this equation, lambda equals h over mv. It's the mass of a proton. Instead of in part A, we use the mass of an electron. And we get 5.46 times 10 to the negative 13 meters, or 546 femtometers. The last problem of this set, number 87. Cosmic rays with photons of an exceedingly large 10 joules of energy. Find the wavelength of such a photon. Energy is 10 joules, so we do wavelength equals Planck's constant times speed of light divided by energy. Plug in those values, and we get 2 times 10 to the negative 26 meters. We compare that with the size of a proton is roughly a femtometer, 10 to the negative 15, which means this is 10 to the negative 11th, roughly, of a proton diameter, or we could say 11 orders of magnitude smaller than a proton diameter. That's the end of the set for chapter 23.